Sir, now it's
Sir, I get
Good evening, everyone. Welcome. Today, we'll be covering time series topics. So what the time series is, in simple words, if a variable can be arranged in some chronological order, in some sensible order, then they can be considered as time series. It need not be time. If there is some inherent order, then you can call it a time series, and time series method will be applicable. And the methods of time series can be applied everywhere. People in finance, specifically economics, in marketing as well, you need to find out like how your advertisement and sales and other variables are related. Then they also can use it. Then people in tourism as well, they may find out how the tourist flow is influenced by variables, let's say exchange rate or the cost of medical tourism, and similarly other things. So the methods are widely applicable for people belonging to different fields. Before going ahead, let me describe a few concepts. Let's talk about first the concept of a lagged variable. Just look at this table. Let's say this is the price of a particular variable for several years. In 2011, the price is 113, then 2012, it's 123. Then in 2013 is 135 and so on. Now, when we say the lag of this variable, then what we do, we basically shift values one period ahead, like this. The first column is the original values, and the second column, that is the PT minus 1. And we denote it by PT minus 1. And you see the first value will be missing. Because 113, that is the value for 2011, value for 2012, the lag value for 2012 is the value for 2011, and so on. So one value, this is how one value is missed. Now we can just extend this concept to multiple lags. So lag for 2 periods would be like this. Look at this. One second. Okay, price lag 2 periods. So look at P sub t minus 2, that is PT minus 2. This is the data which is lagged 2 time periods. So when we lag it by 2 time periods, 2 data points will be missing. And it represents missing values. So this is the basic concept of lag. In time series, we start our basic analysis by considering that a series can be forecasted on the basis of its own past. Think it this way, like there is some momentum in values. When you are selling, your sales are going up, then it continues to rise for several months. Similarly, when a company spends on advertisement, then the impact of advertisement is felt for several months. We can't say that if you are spending in the month of January, then the advantage of advertisement will be limited to this month only. Rather, the impact, the effects, they will be felt for several months to come. So this is the concept of lag. So we start with the basic univariate analysis, like how a series can be forecasted on the basis of its own values. Recall, we talked about multiple regression or basic regression. There we have two variables, X and Y. We forecast Y on the basis of X, or maybe we have many X variables, which becomes multiple regression. But suppose we want to forecast Y on the basis of its own past values, then this becomes the matter of univariate analysis. Now, what kind of models can we make in univariate analysis? Before going to it, let us discuss some more terms. This difference operator. This symbol, which looks like a triangle, this is Greek capital letter delta. And when we say delta YT, it means you are subtracting a value, subtracting previous value from the current value, YT minus 1. So this is the concept of this delta operator, or we call it difference operator. So let's talk about the kind of model that we can encounter when we are dealing just with univariate. Okay. So we have like several kinds of models, and most popular being exponentially smoothing, and second, ARIMA class of models. Exponentially smoothing are basically, as the name suggests, it is some sort of a weighted average of a variable, weighted average of the past values. And we call it exponentially smoothing because the weights decay exponentially. The recent observations are given more weightage, and the values which are in the past, they are given less weightage. And its similar technique is ARIMA. ARIMA is more popular compared to exponentially smoothing because they have like more parameters. And you can say they are complementary to one another. Sometimes they compete. People try to compare the performance of exponentially smoothing models with autoregressive ARIMA models. So we'll discuss these models in detail now. And we denote it by autoregressive integrated moving average models. So ARIMA has three components: AR, then I, then MA. We'll quickly discuss about it. And when do we use them? When the structural model is inappropriate, means we don't have proper explanatory variables. We do not know what are the variables which influence our dependent variable. When we do not know, there is no theory, no reasoning, then what we can do, we can try to forecast a variable on the basis of its past values. But one thing should be considered, that this has to be time series data, because then only we can talk about the past values. If you do a survey, you collect data from 100 respondents, then there is no concept of lag. It doesn't make sense. Okay. So you have price, you have values of GDP for several years, that would constitute time series. There you can apply it. Let's discuss briefly some notations. We will talk about stationarity quite a lot. In time series, your variable should be stationary. We distinguish between two kinds of stationary processes: a process which is strictly stationary and the process which is weakly stationary. So let's first see what is strict stationarity. If the distribution does not change over time, means its mean, its variance, its skewness, its kurtosis, then even the higher order movements, fifth moment, sixth moment, means all the moments, all the characteristics of a series, if they remain constant over time, then we describe them as strictly stationary. It is difficult to find out series which are strictly stationary. So for practical purposes, we are comfortable with weakly stationary processes. We are comfortable with weakly stationary process, and only three conditions need to hold. So weakly stationary means covariance is stationary, and three conditions are needed for a series to be weakly stationary. Expected value of yt is mu, its mean is constant. Okay, look at the second equation, expected value of yt minus mu into yt minus mu. So this is the formula for finding out, for defining variance for population when you have a probability distribution. So expected value of yt is something which denotes mean, and this expected value of yt minus mu into yt minus mu is the formula for variance. It simply says that variance should be constant and finite. And look at this third one. So why T1 minus mu and T2 minus mu? Means we have taken values of y at two time periods, two different time periods, T1 and T2. Means the second values are with a lag. That lag can be for 1 day, for 2 days, for 3 days, or for many days or many time periods, right? So this is also constant, right? So this is the formula for covariance. And because we are using only one variable y, and its past values to describe this covariance, we call it properly autocovariance. So, in short, remember three things. Not zero, constant mean. So, constant mean, constant variance, and constant autocovariance structure, right? So, if these three conditions hold, then we say our data is weakly stationary. I think I should not go into the equations, rather go to the application part. Okay. So the way we define autocovariance, similarly, we can define correlation. Correlation is linear association between two variables. So we have X and Y. We can find out linear association, and correlation is defined as covariance divided by a standard deviation X into standard deviation Y. But in the present case, we have only one variable Y and its past values. So in this context, we would be calling it autocorrelation. Means correlation of Y with its own past values, and we denote it by the letter tau. Here these gammas denote the autocovariance, and this gamma 0 is variance. So we may define the tau s, that is the autocorrelation at a particular order s, is covariance at that lag, that is gamma s upon gamma 0. So what we can do, we can plot autocorrelation for several values. We can take lag 1 and find out autocorrelation. We can take lag 2 and find out autocorrelation. This way we can compute autocorrelation at several lags. And if we plot them on the x-axis, we plot the lags, we denote the lags, and on the y-axis, we show the values of autocorrelation. The resulting graph is called the correlogram or autocorrelation function. Autocorrelation function. X-axis lags and y-axis the autocorrelations. Now, this is the most important term. What is a white noise process? White noise. So a series which is purely random means there is no discernible structure. Whatever you try, you just cannot forecast it. The values are totally random. This is a white noise. So these are the features of a white noise series. That is, mean is constant. Its variance is also constant. And look at this autocovariance function. Look at this. We want to find out the autocovariance at lag r. Means we take values today and we take values r period back. Then this correlation will always be 0. Okay. And if t and r are equal, then it would simply indicate that you are computing correlation or covariance of a variable with itself that is equal to its variance. So it will always be 0 except when you are talking about variance, in which case t and r will be equal. So look at this. Compare it with the stationary process. Constant mean, constant variance, and its autocovariance is 0. And when autocovariance is 0, its correlation will also be 0, right? We are saying except at lag 0. So for a white noise at lag 0, it will not be 0. Why? Because at lag 0, if you're computing correlation, it will always be 1. Lag 0 means you're trying to find out correlation of a variable with itself. At lag 0, it is meaningless. It will always be 1. Correlation of a variable with itself is always 1. So, mind this. white noise process, all the observations are uncorrelated. So if you make a correlogram, you will find only one at lag 0, then all other autocorrelations would be virtually 0. Then this assumption is needed to find out whether autocorrelations are significant or not. Because we know if something is normally distributed, then plus minus 1.96 sigma covers 95% of the values. So our autocorrelation are distributed normally. Okay. So autocorrelations are normally distributed with a mean of 0 and with a SD of 1 over square root t. Okay. So we can use this concept to find out whether autocorrelations are significant or not significant. So simply whenever the value of autocorrelation is beyond these limits, plus minus 1.96 into 1 over square root t, then there are other tests as well. Like sometimes we want to find out whether all the correlations are collectively 0. Recall that when we have to test the significance of a single variable, then we make use of a t-test. But when we have to find out whether the overall model is significant or not, then we make use of f-test. That is the joint significance. Similarly, we want to find out whether a particular correlation, particular autocorrelation is significant or not, we can use the above equation. But if we want to find out whether all the lags are 0, then we can make use of portmanteau test or this box test, Box-Pierce test, then Lung box test, then Box-Pierce test. Then this is the Q statistic. Again, these formulas are not important, not at all important. Software will compute for you. Then Lung box test. This is just a variant of Box-Pierce. Let me show you a very quick example. Okay, so let's say you had 100 data points and you computed the 5 autocorrelations. So these are the lags and these are the autocorrelations. At lag 1, it is 0.207. At lag 2, minus 0.013, then 0.086, and so on. So we want to find out whether autocorrelations are significant or not. Lag 1, lag 2, lag 3, lag 4. So we can use the same concept that we just learned. That is the autocorrelation if they are within plus minus 1.96 into 1 over square root t, means this limit. So solve it. Okay. Okay, so whenever your correlation is beyond this limit, as per this rule, if your correlation is less than minus 0.196, it will be deemed significant negative. When it is more than plus 0.196, it would be deemed positive and significant. So look at the table above. Our first autocorrelation is 0.207. It means this one is significant, right? But look at the other values. The other values are more than 0.196 or less, or they are between these two limits, minus 0.196 and plus 0.196. And see, how do we get these values? How do we get these two limits? That is 1 minus 96, 1.96 into 1 over square root of t. Okay, let's talk about the main processes. So in ARIMA, as I mentioned, there are 3 components: autoregressive, then integrated, and then moving average. I'm starting with moving averages. Moving average process. So imagine we have a white noise process that is UT. Then look at this. Okay, so how YT has been defined in this case. YT has been defined as theta 1 ut minus 1 plus theta 2 ut minus 2 up to theta q ut minus q plus ut. So Y is a linear combination of several white noise processes. So whenever we express something as a linear combination of a white noise random variable, then the process is mathematically called a moving average process. There is one more moving average that you all must be familiar, where what we do, let's say we are taking a 5-year moving average. So we add the 5 values, divide them by 5. Then we shift the window. So first year 1 to year 5, then year 2 to year 6, then year 3 to year 7, and so on. That moving average is different. This is the stochastic version of that moving average, and we call it a moving average process. YT depends on the past errors. Now a question arises, how do we know that only previous 2 errors are important, or 3 are important, or 5 are important? So we need to understand that what is the order of this process. In the present case, there are Q values. So its order is Q. So we can also write it this way. So let me quickly introduce this particular symbol. We call it the lag operator. So L into YT is YT minus 1. And L square YT is YT minus 2. And this L to the power of I, YT equals to YT minus I. And in some books, we will find the operator is the backshift operator. So they denote it by B. They are just synonymous, same to same, just symbolically they are different. Right? So the purpose is to generate lags. So these are just the alternative ways of writing the equations. One second. Look at this. This is an example autocorrelation function of a moving average process. So how can we determine whether a series follow a moving average process or some other process? We can make correlogram, we can look at the autocorrelation function and the partial autocorrelation function. They can guide us. So we'll see shortly, like in the present case, we see that on the x-axis we have lags, on the y-axis we have autocorrelations, and every lag some vertical lines are drawn. Sometimes they are positive, other time they are negative. So these are the values of the autocorrelations. So look at the graph. We also have the blue dotted lines, blue dashed lines. These are the confidence intervals. The same formula has been used, that is plus minus 1.96 into 1 over square root t. So whenever the autocorrelation is crossing these bounds, we say autocorrelation is significant. So look at this graph. We can see that the first two, lag 1, lag 2, they are positive and significant, and lag 3 is negative significant, and all others are insignificant. So this is how we can find out how many lags are significant. Similarly, we can make a plot called partial autocorrelation function. That is the same plot. The only thing is that we are controlling the impact of intermediate autocorrelations, intermediate lags. Okay? Intermediate lags, if we control its impact, it becomes partial autocorrelation function. Then the second class is autoregressive models. So what is an AR1 model? So name itself suggests autoregressive, means Y depends on its past values. So YT is equals to mu plus phi YT minus 1 plus UT. YT minus 1 is the past value of Y, and phi is like how important is the past value for today, YT. Similarly, we can have a model for order 2. So phi 1 YT minus 1 plus phi 2 YT minus 2 plus UT. This is of order 2, means previous 2 days information is important. Then we can say that past p values are important. And we can denote it by this way. Or we can also denote it this way. Using summation notation, summation from I is equal to 1 up to p, that is phi I yt minus I plus ut. These are just ways of denoting it. Or we can make use of the lag operator. So what we can do, we can take this entire process to the left hand side. And if we further solve it, it becomes this. So you can take common. This last thing is important. This phi L. So phi L yt is equals to ut. So what we have done a little algebraic manipulation. See, that means these mathematical details are important, but not very important. From a practical point of view, they're not extremely important. But yeah, for understanding like what impact will it have. So we are just quickly going through this. So phi L can be extended to give us something called a characteristic equation. Basically, when we develop an AR model, sometime it becomes an explosive model. On other occasions, that means something implausible. When it is explosive, it means it cannot be used for forecasting. So how do we know? So we will have to look at the characteristic roots. Again, that equation will be time consuming to discuss. So I'm not going into those details. So this one is important. Stationarity. Recall a few minutes back, I talked about what is stationarity, and we are concerned with a weakly stationary process, a process whose mean, variance, and autocovariance are constant. That would be a stationary process. So how do we know whether a process is stationary? So whenever you develop an autoregressive model, then what we can do, an autoregressive model can always be transformed into a moving average model. Autoregressive model can be transformed into a moving average model. And if it is possible to transform, then it is said that the models are stationary. And vice versa, a moving average model can be converted into an AR model. When this is the case, we say that it is the model is invertible, right? So stationarity and invertibility, they are similar conditions, means you're able to derive MA from AR or vice versa. So like this, yt is equals to phi L to the power of -1 into ut. This phi L -1 will be a series of coefficients for ut. This will be used extensively. And this is our characteristic equation. I'm not going to discuss it. Just you need to remember this. For a stationary process, all roots should lie outside the unit circle. Right? But in some cases, the characteristic equation is defined the other way. In that case, roots should be inside the circle. So you need to consult your software the way it has been defined. Let me quickly talk about what is a random walk process. Yt is equals to yt minus 1 plus ut. It simply says that something today, a variable yt today is what y was yesterday plus a pure white noise random term. Yes, please. Are you asking something?
अच्छा ठीक है भैया वो बुलाते हैं
Kindly mute your mic.
All the participants are requested to mute their mics. If you have a doubt, only then please switch on your mic. Thank you.
Okay, so whenever we have a random walk, then the feature of random walk is that the impact of past errors always stays the same. So not good for forecasting. I'm not going into the detail, I'm skipping it. 1 second. Then we have these, the combination of autoregressive and moving average things. So look at this ARIMA process. So we have yt is equals to mu plus phi 1 yt minus 1 plus theta 1 ut minus 1 plus ut. So both things are important. Past values are important as well as past errors are important. So this is ARIMA 1 1. ARIMA 2 1. In ARIMA 2 1, what we have? Two values of y and one value of error, one past value. Or ARIMA 1 2. In ARIMA 1 2, we have just one past error and two these errors. One past value of y and two past errors. Okay, now let's jump to the modeling part. Like, how do we know? We have discussed quickly the three kinds of processes: autoregressive, moving average, and a combination of these two. Then how do we know the variable is following which process? So let's open RStudio.
Atif sir? Atif
Let's
sir?
quickly model them.
Atif sir, am I audible?
Yes, you are audible.
Just 1 minute, an announcement for the participants.
Please.
Please join this meeting by your actual username. Because we are noting down the attendance and there's somebody whose name is Concept Learning Classes. So please join by your actual username. Your registered username. Thank you.
Okay. Okay. I think all the 4 pins are visible. So we'll be working with the univariate data set that I have provided. So let's open the code file. Okay, let's look at this data set. 1 second. So this library is needed. I forgot to tell you some packages we'll be needing today. Okay, so during the course of our discussion, you will get to know this forecast package would be needed. So let us read this data, univariate processes. Then tidyverse, load the package. Then there is one more package that I'll be using today. There is Lubridate. Basically, this will simplify your task a lot. I have been working on R for more than 10 years. And initially, date used to trouble me a lot. That means how to work with dates. So Lubridate is an excellent package that would simplify your task of dealing with dates. So it has inbuilt functions to extract like weekdays. You want to remove the data of weekdays or other stuff on or weekends, or you want to extract just the you convert them into other format. So Lubridate is the function that is quite handy. Is a package that is quite handy. So let me just show you some of the data. Look at this. If I type str, how the structure is 1000 observation of 6 variables. $date. Look at this. The first variable is date, but it is saying it character. Okay. Character. It means before using it in time series plots, I need to convert it into date. Then x1, x2. Okay, I have 5 more variables named as x1 through x5. So what is the first task? I need to convert this character date into proper dates. And look at this function. This is a great function. So I did not define this symbol earlier. df dollar. Basically, this dollar operator is used to refer to a particular column. When I say df dollar date, and this is on the left hand side to the equals to sign or assignment sign, it means I'm asking it, take the data frame, take the data set df and create a new column date. So dollar is either to refer to a column or to create a new column, or even to delete a column, we can use this function. That dollar is to refer to a particular variable. What does the function say? Df dollar date equals to parse date time, right? So if I do not know the format of my date, and basically I've seen most of the time people commit error or like they face problems because they copy data from several sources. As a result of this, their date format is changed. Initially, some dates are like as date, month, and year. Some other time dates are like, let's say in alphabetical JAN -02. So month has been represented with the help of letters, and other numbers are numeric. Month and year are numeric. Sorry, day and year are numeric, and month is in letters. So all these problems can be handled easily using this function, parse date time. I'm asking this function that take this column, take the column df dollar date and convert it into dates. And I'm just giving you it some hints that what format my dates can have. My dates can be in date, day, month, and year order, or it can be in the reverse order, year, month, and date. So let's do this and see what happens. Before that, let me show you what were the original values of date. So let me just show you head of df. So look at this.
Hello, sir.
Again. Yes, please.
Sir, have you shared this codes for Univariates?
A code I did not share.
Yes, thank you.
So did you want the code side by side? I thought I should explain
Sir,
first, then I'll be sharing it.
Oh, yes, sir. This will be easy for side by side, no, sir.
Okay, you could have told me earlier. Yesterday also I did not send. I thought that this is a better way. 2 days back, someone told me it's better that I should do on the screen. You can ask questions and later on you can do.
Okay,
Sir,
sir. No
both-
problem then.
Both
No
will
problem.
be important, sir. Side by side as well as whatever.
So
you-
should I send it right now?
Yes, sir. Yes, sir.
So
Could
just
be
tell me. I think there is a way to share it on Zoom as well.
Through chat you can.
Sir, through chat you can send, sir.
Should I copy the
Sir,
entire code or
preferably-
just share this file?
Sir, preferably by mail. Zoom, though you have to download immediately. Otherwise, you won't be able to trace the data.
Okay.
If it
so
is through mail, it will be there, na? Even if
just a
it,
while.
for people who are not going to do it now.
So just a minute. I think,
Yes,
should I
thank
stop the
you.
recording for a while?
Yes, sir, you can send it by stopping.
I think I cannot stop that. Just wait. I'm just, but I do not have your email IDs. I'll send it to conveners. One second. One second.
Atif sir, is there any issue?
Yeah, I have to send some data, some codes. So I'm sending it. I'm emailing you to you.
Okay.
So codes. One second. So first respond. Okay, I've shared 3 code files with you. Ajay
Okay,
sir,
sir.
kindly share these codes to
Okay.
with the participants. So,
Just I need to share.
yeah, just email them. Yeah,
Okay,
I've
sir.
emailed you right now.
Okay, sir.
I just emailed you. Okay. If I knew it, I would have shared them earlier as well. So it's my mistake.
Yes, sir. Thank you, sir.
Okay. So, okay. But remember that before loading these packages, you need to install them. So if the packages are not available, Lubridate is automatically there when you install Tidyverse. In case it is not there, you can install it again. So Lubridate, then Forecast, there will be several other packages. So once you see a package that is not installed, or if it throws error, then you need to install it. Not a big deal. Okay. So look at this. So look at date. 01/01/2017. It is in day, month, date, month, and year format. But the R way of storing date is the other way, right? It stores date in other format. That is the YMD. Let me show you. Look at this. So I have converted it. And now let me show you the structure. Look at this. Now it says POSIXCT. So that is one of the formats of time, date and time. And now our date is proper. It says POSIXCT. So if the function says POSIXCT date or IDate, so anything, if you find date, then it means this one has been properly formatted. Okay, and let me print it. How does it look now after converting to date? You see, YMD, year, month, date, then hours, minutes, and seconds. Okay, so let's see what the code is gonna do. Let's plot this x1. Okay, so you see that x1 has been plotted. And I'll discuss shortly that this graph moves around a constant mean. So chances are very high that this one is stationary. We have a specific test for it. Graphically, it appears to be stationary. Let me do one thing. By the time you just download the codes and install the packages, should I discuss the theory behind quickly the technique of how do we test for stationarity or the concept of unit root?
Yes, sir.
I think I should quickly
Yes, sir.
discuss it. Right?
Yes.
Then
thank you.
I'll come to it again because ARIMA modeling is applicable when your data is stationary. So I think the meaning of I would be clear then. Let me quickly go back to that. Okay, before that, let me tell you that what we do in ARIMA, basically ARIMA modeling is a 3-step process. It is a 3-step process. One. So step 1, we identify whether it is an AR process or moving average process or a combination of the two, right? Means we determine the order of P and Q. P means how many lags of Y and Q means how many lags of the error term. Then we estimate the model. And then we do the diagnostics. Similar to multiple regression, identification means we determine the model, we identify the independent variables, then we estimate using OLS or maximum likelihood or the instrumental variable approach, whatever. And then lastly, we perform some diagnostic to find out whether some pattern remains in the residual. If some pattern is there in the residual, it means model is misspecified. Okay, so before going to step 1, let's talk about what variables, what should be the characteristics in data before it is available for univariate modeling. And the concept is stationarity. Let's quickly discuss. Unit root. Look at this model. We call it random walk. And this is random walk with drift. Yt is equal to mu plus yt minus 1 plus ut. Technically, what should happen? Technically, it should happen that the older news should have lesser and lesser impact, because something that is past, it must have lesser impact, and events which have happened recently, just 1 day back, 2 day back, they must have more impact than something what happened 10 days back or a month back, right? But if there is a random walk, if the model is random walk, the feature of this model is that we can show it mathematically that the impact of all the errors is same. Against the common sense says that the impact of past errors should decline. As we go in the past error should become less valuable. But in this model, we can show that the past errors are as important as the recent errors, right? So there is a problem with this model. Then this is called a model with a deterministic trend, where y is a function of time. Then this is the most important concept. We call it unit root non-stationarity. Basically, let's quickly talk about what is the meaning of stationary or stationarity. I've talked about weakly stationary means mean constant, variance constant, autocovariance structure is also constant. So quickly look at this. Look at this model, yt is equals to mu plus yt minus 1 plus ut. So imagine its mean is 0. It will be easier to analyze then. So what we can do, we can substitute for yt minus 1, just like I have written yt is equals to phi 1 yt minus 1 plus ut. You can write, one second. You can write it this way. Yt minus 1 equals to 2 t minus 1. Similarly, you can write out the equation for yt minus 2. So yt minus 2 will be equal to phi 1 yt minus 3 plus ut minus 2 and so on. So what you can do, then you can substitute these two equations back into the original one. And if you keep substituting, then this model will emerge. Okay. And let us not go into the mathematics and go to the results directly. So if a series has a unit root, basically what we can do, recall, I told you that an autoregressive model can be expressed with the help of a polynomial, and that polynomial is the characteristic equation. Now, just like we have a linear equation, we can find out its parameter. Similarly, we have a quadratic equation like ax square plus bx plus c. We can solve it, and we know that the roots of a quadratic equation are 2. There are 2 roots. There are 2 solutions. Similarly, for cubic equations, we have 3 solutions. Okay. So we take the characteristic equation and we find out the roots. Now, there are 3 possibilities. Either all the roots are less than 1, or all the roots are more than 1, or all the roots are unity, right? So these 3 cases exist, and one case we rule out, the case that belongs to, one second, that the root is not root, that this coefficient is more than 1. When the coefficient is more than 1, roots would be less than 1. So if there is one root which is equal to unity, I told you that roots can take value positive, roots can be more than 1, root can be less than 1, right? Or root can be equal to 1. More than one case, less than one case, we are ruling out. If root is equal to 1, then this is a specific kind of non-stationarity that we call unit root non-stationarity. Okay. If it is equal to 1, it becomes unit root non-stationarity, and its impact is that past error always remain in the system. Their effect do not die out. And if a series is stationary, we call it is integrated of order 0. So I0 means there is no unit root in the series, the series is stationary. How can we know whether series has a unit root? Look at this. Yt is equals to 5 and yt minus 1. So by root means, again, as I told you that there are two ways of looking at the roots. In one way, we are saying the coefficients, and the other way is when we take all the variables to left hand side, make the equation and so on. Interpretation would be reversed. Okay. So when somebody say they should be less than 1, if you are doing the other way around, it would be more than 1. So need not worry about the mathematical details. Just look at this. So yt is equals to 5 and yt minus 1. Unit root means the value of phi is equal to 1. If value of phi is equal to 1, it means the error have their impact and it does not die out. Okay. Just do a little trick. Subtract yt minus 1 from both sides. And it becomes this way. So yt, delta yt is equals to then 1 minus of 5 minus 1. Okay. And 5 minus 1 can be denoted by a new symbol, let's say gamma. Now compare the last two equations. In the second last equation, we have 5 minus 1 into yt minus 1. And in the last one, it is simply gamma yt minus 1. So how gamma and the upper one is related? We can easily see that gamma is equals to 5 minus 1. So if gamma is equal to 0, that simply means phi is equal to 1. Okay. So how do we know phi is equal to 1? We can simply do a t-test and find out whether gamma is 0 or not. Okay. But the problem is that when data is non-stationary, then the sampling distribution of gamma does not follow any standard distribution. Rather, it is highly non-standard. And when it is non-standard, it means you cannot make use of the simple critical values. Rather, those values have to be simulated. On the basis of simulation, you will have to generate those values. And some people have conducted like millions of simulations and tabulated the values. Like you see in software, then it is reported like who simulated those values. So the logic is that we just look at this. If it is significant, if it is significantly different from 0, then it is concluded that there is no unit root. And if it is equal to 0, if it is equal to 0, means if the null of 0 is not rejected, we conclude there is a unit root. So this is how we decide. If null is rejected, there is no unit root, means data is stationary. If null is not rejected, then there is a unit root and data is non-stationary. So Dickey and Fuller. Then they gave the test, Dickey-Fuller test, which was later refined to augmented Dickey-Fuller test. And this is the basic equation. So we just look at the coefficient of psi. The symbol is psi, that looks like 3 heads, like 3 arrows. It's psi, PSI, psi. If psi is 0, then we conclude that data has a unit root. Okay, so this was the theory behind unit root. And when we say unit root, then unit root and non-stationarity, they are the same thing. Means if something is integrated of order 1, I1, unit root, non-stationary, these are synonymous. Then stationary and I0, they are synonymous. I0 and stationary would be termed synonymous. Okay, so let's get back to our series. I believe you all must have got this course by now.
Sir, null here is series is stationary.
No, null is that psi is 0. Let me write it down. 1 second. So, and this means data has a unit root. It means non-stationary. So null is there is there is a unit root or there is non-stationarity in the data. Okay, null is of non-stationarity. So null has to be rejected for data to be stationary. Right? This is the case with augmented Dickey-Fuller test. Then one more test has been proposed by Phillips and Perrin. Their methodology is different, but their null hypothesis is also same. Data has a unit root, data is non-stationary. So this is the null hypothesis for and Phillips and Perrin test. One second. What happened? One second. Okay. There is one more test. These three tests we'll be using. We call it the KPSS test. And in this case, null is different. Data is stationary. Okay, so what should be the result? Suppose ADF is rejected, PP is rejected, but KPSS is not rejected. It would indicate data is stationary. Then second case, ADF not rejected, PP not rejected, KPSS is rejected. Then data would be non-stationary. Non-stationary means it has unit roots, right? It can have one unit root. It may have more than one unit root. Most of the processes that we come across, they have only one unit root. These processes have mostly one unit root. On rare occasions, series also have two unit roots. I just showed you the equation a few minutes back that when you solve the characteristic equation, then you get the values of roots. So if one root is equal to 1, we say it is I1. It is I1. It has one unit root. When it has two roots which are equal to 1, then we say it is of order 2. We call it I2, integrated of order 2. Now, what to do with a non-stationary series? Suppose a series is non-stationary. Now, what to do? Before doing any regression, we must make it stationary. And how can we make it stationary? It's quite simple. The process is called differencing. How to make a series? How to make non-stationary series stationary? Answer is by differencing. Recall, I talked about the delta operator, yt minus 1. Means if you find out the difference of a series, that difference is stationary. If series has one unit root, then only by differencing once it becomes stationary. If data has two unit roots, then you will have to perform the differencing twice. On rare occasions, we have to difference twice. In most of the cases, more than 95%, I must say, I think rather I should say 99. In 99% of the cases, your data has just one unit root. Okay, so we know how can we convert a non-stationary data into stationary. Then there is one more type of non-stationarity. Recall I talked about a process which is deterministic, which has a deterministic trend. They are converted into stationary processes by detrending. We estimate the equation of a trend and we find out the residual, and those residuals are stationary. Okay, we'll talk about these things quickly. So let's move on to the analysis. RStudio. So look at this. For the sake of convenience, what I have done, I'm defining this x equals to df$x4. So randomly, I'm taking this fourth series. I'm taking this fourth series and transferring it to x. Okay. One second.
Sir, X4 means it is series 4 of the.
No, not series 4. This is the exact variable. So it can be at 4th place, 5th place, 7th place. Let me show you here. Look at the names in DF. So what do we have?
The variable name itself is X4.
Yes, yes, the variable name is this, right? Otherwise, X4, if you do it in some other data set, it would mean nothing. But if you want to refer to the fourth column, then you can do this way: df left bracket comma 4. So df, that would denote the fourth column. Just like metrics are denoted as rows comma columns, right? I comma j, rows comma columns, right? So it is the fourth column of df. If you want to denote want to refer to the fourth column, right? In the present case, this is the fifth column, right? So df $x4 or this df bracket comma 5 bracket. Please mind the difference. This is a bracket, but all other functions that I have shown you, they are the parentheses, those round brackets. Okay, so let's not run it. Let's get back to it. Yes, so you need this package ARCA, URCA, unit root and co-integration analysis. So before this command will run, you need this package. See, look at the code, the previous lines. Did I load the package URCA? I did not, but I want to use just one function. When you want to use just one function, there is no need to load the package. Rather, you write the name of the package followed by colon, then ur.df. So without loading a package, a function can be used. So let's run it and see what is the result. Augmented decay flow test. Okay, so that means it doesn't tell us anything. So this is not a good command. I must change it. I'm going to it again. So we need this summary of it. Summary. So look at the summary. That would be the complete picture. 1 second. Let me see. One second. Let me do one thing. It's better I should load this library. Okay. Okay. Let's see. Now just go to the last line of the output. Value of test statistic. It's always negative. 17. And what about the critical values? At 1%, 5%, 10%. So you see the values are given to you. And this particular value is much larger. -17 is larger than all the critical values. Conclusion, null is rejected. Means our data is stationary. Our data is stationary. You can do other tests also. And there is a package called T-series. I think I loaded it. T-series package has a function called adf.test. So, okay, error because I did not load the package T-series. I can do this. Okay. You see p-value is 0.01 and there is a warning as well. And the warning is saying that the p-value is even smaller than this. Reason is that in a Dickey-Fuller test, augmented Dickey-Fuller test, or in other types of stationary test, it is not easy to find out the p-value. That's why you will have only approximate p-values. So you can safely say that your p-value is smaller than 0.01. When p-value is small, null is rejected. Okay, there is no unit root. Our data is stationary. So go to the process. Okay, look at this command. It's saying that autocorrelation function of x, and do not plot it. That means I do not want to plot the values. I just want to look at them, what the values are. Let's run it and read the values. Autocorrelation from 1 to 10. At lag 0, it's always 1, understood? This is not important. Second value is important. That is at lag 1. It's 0.41. Lag 2, 0.17. Lag 3, minus 0.09, that is negative. Then fourth value is very small, very small. Let's present it graphically. Okay. Do you see a graph?
Sir, you scroll down a bit, sir.
1 second. So 1 second. Is it visible now? 1 second.
The tab is open. Yeah, yes.
Is it visible now? Graph is not visible. 1 second.
So if you could maximize the screen, that also.
It was not maximized. 1 second.
Yes.
But now? The right side. 1 second. 1 second. Okay. Is the plot visible now in the bottom right? We can enlarge it.
Yes, sir.
Okay. So this is the autocorrelation function. You see the first 3 lags are significant. Initial 2 are positive significant. And how do we know the significance? The blue dashed lines, the autocorrelation is crossing them. So we can suspect that, yeah, there is autocorrelation. Okay. Now look at the other plot. So I think all the 4 panes are visible now.
Yes.
Okay.
Yes, sir.
Let's plot the partial autocorrelation function. So partial autocorrelation function, sometime positive, negative, and like it is exponentially decaying, but it is just changing sign. Okay. So now what patterns can we have? We can have 2 patterns. ACF and PACF. If ACFs are significant to a particular point, then become 0, and partial autocorrelation are like exponentially decaying. It means this is a moving average process. On the other hand, if autocorrelations are exponentially decaying and partial autocorrelation are significant to a particular lag and then cuts off, it becomes an AR process. And if both of them are like decaying exponentially, this becomes an ARIMA process. But see, this is very tedious exercise, means graphs are never so clean to analyze and they are subjective in nature. So our process will be simplified if we have some like test statistic and we have this function called auto.arima. What the function will do, it will compute the AIC. That is the Akaike information criteria, then Schwarz information criteria and other criteria as well. And the criteria that has the model which has the minimum value, that model is chosen as the optimal model. Anyway, we looked at the graph and the graph reveals that our process is moving average 3. Let's see what does AutoArima tells us. So auto.arima, let's run this. Okay, let's see the output. 003. What is this 003? It has 3 components, AR, then I, and then MA. So AR is 0, I is 0. Why I is 0? Because our data is stationary. And 3 means MA3 process would be the right approach for our model. So, and the same thing is substantiated by looking at the graphs. Okay, so we can now develop this model. So let's make this model M equals to ARIMA followed by the name of the data set, and then we specify the order. Order equals to C003. Okay. And if you want to include the intercept, you may include, otherwise you make it. This T means true. You can write the entire word TRUE all in caps, or you can write simply capital F or complete FALSE all in caps. So just run the model and you can then run the summary. Okay, and this is the summary of the model, and these are the coefficients: MA1, MA2, MA3 intercept 0.46, 0.464, 0.27, minus 0.14. So we have these three coefficients. Two of them have positive impact, third one has negative impact. And we have a lot of other information, a standard error, then the standard error of the estimate. Okay, then this is the like model diagnostics are also there. Not diagnostic, I must say this is the performance of the model. So this is the mean error, then root mean square error. When you want to compare between models, then you can compare these statistics. So you may fit, instead of MA3, you may fit an AR1 model and you can then compare, right? And it is calling it a training set. Why training set? Basically, in real life, how should we do? We should divide our data into two parts. 80% our data for modeling and 20% testing how the model performs. So we call it as hold out sample or out of sample forecast, right? I won't be able to cover everything today. I'm just leaving it. So we're moving on to the next thing. So we have done two steps. We have identified the order, identification. We have MA3. Then we have estimated the model. And now diagnostics. So diagnostic means if everything goes well, there should be no pattern in the residuals. And how do we know there is no pattern? 1 second. One second. A second. Okay, so what we have like some functions called box.test. Okay. 1 second. Okay. 1 second. So we need to do it on residuals rather than doing on the model. So box test is the same that I told, that is the like box PS test or the lung box test. Let's run it and look at the result. P value 0.71 means null could not be rejected. It means there is like no autocorrelation in our data, means our model has done a reasonable job of capturing everything. So this value should be large. When P value is large, it means our model is good. And see, this one is a very interesting function. Simply run it. It will give you three plots. The plot of the residual, then their autocorrelation functions, and it do gives the histogram as well sometimes. Let's see what does it give. So it gives, I think, three plots. Okay. And you can see that means no lags are significant as such. So this is a graphical test. And it does display some statistic as well. Okay. I think we have spent enough time on it, right? So let's move on to the next thing. Before that, just let me take some queries. Any query regarding univariate modeling?
Sir, after executing this command like ARIMA X order C
right
003, we got some coefficients.
Right.
So when we write those coefficients as a model, so we write intercept plus UT minus 1 into that coefficient, then UT minus 2, UT minus
exactly.
3.
Exactly.
Right.
Right.
Okay, sir.
Fine. And I did not discuss some more commands like now the story begins. Afterwards, we go on to forecast. So I'll do one thing. I'll just share some of the functions for forecasting. You can just play with them. Right? You can see how can you use them for forecasting. But yes, this is univariate analysis. Now let's extend this concept. Like we are forecasting one series on the basis of its own past values. But what about we forecast one series not only on the basis of its past values, rather the past values of other variables? Think about sales. sales depends on its own past values. But don't you think the model would be better if we include the past values of advertisement as well, or past values of R&D as well, right? So that becomes a vector autoregression. Vector simply means vector is a collection of objects, right? So just like we have one value, vector has, you can say, a collection of more than one variable. So everything remains the same. The only thing is that the single variable is replaced by a group of variables. That becomes vector autoregression. So we are moving from this AR to VAR, vector autoregression. Let me just quickly show you a few equations. One second. This is your VAR. One second. Okay. Give me a moment, I think. Okay. Okay, vector autoregression means there are more than one variable. So more than one means there can be two, there can be three, there can be more than three. So let's start with a bivariate VAR. We have two variables. Bivariate VAR. The model looks like this. So two variables, and each variable is dependent on one past value of the other variable, including own. So look at this model. So this is yt is equals to, it's phi0 plus alpha 1 yt minus 1 plus beta 1 xt minus 1 plus ut. Then we have equation for xt as well. So both the variable depends on the past values of one another. Just mind one thing, these kind of models are called as dynamic models. Means not just one time period is involved, rather many time periods are involved. Today is involved as well as yesterday is involved. This is called a dynamic model. And notice one thing, there is no variable on the right hand side which has subscript time t. You see, yt minus 1, xt minus 1. We do not have xt on the right hand side. Can we have xt on the right hand side? Of course we can have. In case we propose that the current value of xt influences the current value of yt, we call them the contemporaneous term. Means the right hand side variable are having the same time as the left hand side variables. Those are called contemporaneous, measured on the same time, measured at the same time. Okay, so bivariate var 1 then this is bivariate var 2. So equation is quite simple. Now two lags are important. Okay, similarly for x as well, two lags are important, and we can extend it to p lags. This is p lags. Okay, for x as well. So x depends on p values in the past of y and p values in the past of itself. Okay, but we can write it using summation notation. You can interrupt me in case you have a query. Then we can have a trivariate var. It means three variables. So it looks like this. The concept is similar. So trivariate var 1. Yes, symbols are different. Okay. So y2t, y1t, y2t, y3t, and all of them are called these y1t, y2t, y3t. These are endogenous variables, and their past values y1t minus 1, y2t minus 1. These are predetermined values, because if I talk about today, then I have all the information available till yesterday. Okay, so y1t minus 1 or y2t minus 1, these all are predetermined variables. These are the lags. Okay, so this is how var can be generalized, and there are several ways of writing this. Like instead of writing it equation by equation, we can write it like in matrix form. Let me just show you quickly, 1 second. Look at this. So this is another way of writing out var. So these are just ways of presenting the same information. One second. Okay, you see y1t, y2t, and the equation becomes very weird. But yes, these are the ways of describing things. Okay, so let's move on to modeling of var.
Sir,
Let's
here
go to-
y1, y2, y3 are three different independent variables?
Yes. No, not independent. All of them depend on one another. All the three are endogenous variables. They depend on one another. Y1t, y2t, y3t. Let me go there.
Like sales, advertisement, and
Yes, exactly. They can be sales, advertisement, R&D, or
okay.
maybe sales in city 1, sales in city 2, and then maybe the GDP.
Okay.
Right. Or you can denote it by this way. Just this is a succinct way of writing it. So YT, it is a 3 by 1 vector, means it contains 3 elements and there is just one column. Okay. So in case you have a query, you may ask if you want me to explain this particular way of writing. Okay, so mu is again a vector of 3 elements because we have 3 variables. If we had 5 variables, it would be 5 times 1, 5 by 1. Okay. Okay, this is how we can represent the stuff. And there are like other ways of writing out these equations, but they all are identical. Just forms are changing, concept remains the same. Okay. Okay, so now let's take some real examples. And this example I have borrowed from this book called Lutkepol, one of the finest books. This is the new time series, right?
So Lutkepol title is what, sir?
And this is the new time series.
New time series, okay.
Yeah, I'll provide the exact title. I'm just missing it. It's something to this introduction to new time series or
okay.
New time series. Yes. Let's open this new code. So the code file is impulse response.r. I believe I have shared this code file. Impulse response.r. Okay.
Yes, sir.
One second. Yeah, now we need some more libraries. We need this XTS and VARs. Okay, so kindly install these packages in case you don't have VARs. Everything is in small. 1 second. I'm closing this code univariate, right? Or let it be. How does it affect? Okay. So impulse response. And see, let me tell you very interesting things. Now look here. And that creates error number of times. So I'm running this command, library was. Right? I'm doing one thing. I'm just closing the session and I will reopen it. I want to show you something. Don't save. R Studio. The first one is library XTS. Okay, I've run it and see that it gives some output. That means it shows like what functions are available or what functions are masked. Certain functions are masked. Mask means suppose there is a function called filter, right? This function is there in one of the packages of tidyverse and the same function is there in vars, right? So it means R can use just one of them. Similarly, there is a function called as.date. This function is in 2 packages, package stats, which is always available. Then this package XTS. Now only one of them would be available. So in case you want to refer to a specific function, then you need to specify it using that colon operator, so that if you like face an error, then most probably the reason is that if you load the packages in different order, then your code may need a little revision. I'm just telling you that sometimes initially when I used to work, there used to be several errors, and I used to figure out that the main reason was it was the order in which packages were loaded. So sometimes this is informative, that when we read this, when you load the packages, then it says something. The following objects are masked. So earlier I was in the habit of not reading this, but now I do, because when I am writing explicit codes or detailed analysis, then yeah, this information is important, like which functions won't be available, right? So as a safer side, what I like do in most of the cases, I always use this.
Sir, excuse me.
Yes, please.
Sir, can we have need to run the more than one packages for one for one function? Like right now I'm trying to this var, so they are asking for mass, structure, chain, sandwich, URC, LM test. There are three things they are saying loading required packages.
Yeah, that means of course all these packages will be needed, because
So
of
there will be
var.
more than one, right?
Yeah, because one package depends on so many other packages. Look at this
Okay.
tidyverse. Tidyverse, I think it comprises of I think more than 20-30 packages.
Okay.
So there are dependencies. It loads automatically. See, once you install a package, you see, let's look at this. One second. One second. It's not there. One second. Okay, it will not work. There are some other shortcuts in place. Okay, so once you go to this, your tools and click on install packages, there you would see there is a checkbox, install dependencies. So kindly do not uncheck it, because in that case, if you do not install the dependencies, then the package will not work.
Install dependencies.
Okay. Library XTS, library wars, library tidyverse, library series. Okay. Guys, now look at this command. This time I'm using a different command. This one is in fact, I would say more efficient than read.csv. This is called read_csv. This is from a package called tidr, and this tidyr is part of tidyverse. So sometimes I use this command. So right now I'm using this command, okay, to read this file. Okay, I have loaded the data. Okay. So it gives me immediately that what do I have? 4 variables and 76 rows. And see, date is in character. It means I need to convert date into proper dates. So, yeah, one more thing. You need one more package today. This is called anytime, any date. Sometimes what happens, like, let me show you the data. Why do I need this package? So look at the head of DF. (1960-01), 1960-02 means we have just 2 components, right? The third component is missing, right? The third component of date is missing. So it is like we need to understand what is it. So either you need to provide the proper dates, right? Or you need to, like, you can make use of some package that would automatically convert it. There are like several ways of doing it. So I found this one easy. I use this df$date. So let me see what it does. Basically, these are wrong dates, but anyway, this will not impact our analysis. I'll show you, I'll just refine the code and we'll share again. Basically, this data is quarterly data, right? So it has not been picked up properly. So there is a different function for it. I'll share later on. But right now, focus on the analysis because it won't change. Okay. 1 second, what we have. So first of all, what we can do, we can take log of all the variables. 1 second before that. 1 second, there is a error. One second. Okay. Now look at this command, what this command is doing. It's creating a new object called df1. And df1 is in a format that would be XTS. I did not talk about this package. You also need this package called XTS, right? And this is a wonderful package when you're working with time series. It can make working with time series very easy. Means there are certain inbuilt functions that can be used. So we could like spend several hours on learning this package. This package is wonderful, XTS. So let us convert it to XTS object. So, and see, if you do not have time to learn these specific packages, then like you did not invest time on that. The code I'm giving it to you, I'm sharing with you. Use these codes, just change the names of your variables and names of your data files. Most of the analysis would remain the same. So you just need to change the names of the variables and just read the proper data files. Okay. And see, I think in your case, maybe one of the commands may get an error, like while loading the data file. Look in the present case, what I did. You notice that till yesterday, I was using the function called file.choose, right? But today I'm not using it. Why? Let me show you when can I use it. Let me tell you first. See, I have written directly read_csv quotes, the name of the file, right? So if you're doing it, then you need to make sure that the path is specified. Right now, my working directory is documents. My working directory is document. Let me show you. How do I know it? Get. Okay. You see, my working directory is documents, right? Means if I write any file name, it will be searched in documents. If this file is available in documents, it will be loaded. And if this file is in, let's say, downloads, then R will throw an error like no path exists. So as an advice, better thing is that do not use this command, use the same process file.choose, right? File.choose. What you're going to do, instead of this file, which is written in the quotation mark, simply replace it by file.choose. Okay. If you're following along, then you may run into an error, or put the file in your documents folder. Okay. 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 XTS has been converted successfully. Then log. And see, this is a good function. See, what I've been telling you, that why do we need R when there are we have other software like eViews, Stata, and like they are much easier than R. At least it seems so. But what you can do with R, you can just produce reproducible codes and which are really fast. So see, like how many variables are there in my df1? If I show you, look at this. Right now, there are just 3 variables, but maybe I'm working with 5 variables or 10 variables. 10 variables. And if I need to perform unit root test, then I need to run unit root test 10 times, right? That would be quite time consuming. So what I can do, I can take this command, laply. Laply means apply list wise, means apply on each column. It's saying that take the data df1 and take the function from where? From this package series. and compute ADF test for every column. Let's quickly do it and see what do we get. So $invest ADF test, and what is the conclusion?
Non-stationary.
P value 0.25 non-stationary. So you can just check all the 3 series are non-stationary. So what we're going to do, take difference. So this is the power of XTS. You just specify the object into it, and like operations will be performed on all the columns. So let's compute first difference and let's call it, we are calling it DF2. You see right now I have used less dash. No need for this. You can simply write equals to. So less dash is an assignment operator. You can use equals to, no problem. So DF2. Again, find out unit root test for DF2 means now what I have done, I had already taken the log and now I have taken first difference. Why do we need to take logs and why we are taking first difference? First difference makes our data stationary. And if we have already taken log and now we are taking first difference, the interesting thing is that the first difference of log is percentage returns. They are continuously compounded returns. So this is why you see in all the empirical applied work, you always take log and then take the difference so that the difference has some meaning, right? So log and then difference becomes percentage data. So now we have percentage change of investment, percentage change in income, and percentage change in consumption. So let's run this test. Again, Lapley DF2. And now I'm not using that test. I'm using now KPSS test. And remember that what was the null hypothesis of ADF? It was data is non-stationary. PP test, data is non-stationary. And KPSS test, data is stationary. KPSS, data is stationary. So DF2 should be stationary. I've taken first difference, quickly run it. And just quickly see, kindly verify, what are the p-values? I think they all are 0.1. Why 0.1? 0.1 is that because p-values are approximate and they cannot compute the precise p-values. The only thing is a warning that p-values are larger than this. Okay, when p-values are large, null hypotheses are not rejected. Means this DF2 is stationary. So instead of KPSS test, you can, there are several other tests like Andrews and Zwitt test. Then we have this ERS test. Then we have what we say Phillips parent test, and other tests are also available. You can just try with them. Okay. Now let's move on to the modeling part. We're going to the VARs. Again, same process.
Sir,
yes,
before moving, in line 9 in STS, what is this -1, sir? Within
-1, yeah. Basically, what we are doing, when I take this data frame DF, it has got 4 columns. First column belongs to date, and my real data is in remaining 3 columns. Okay. So when I convert to XTS, XTS says that only numerical data is allowed. Dates are not allowed. So I am just dropping the dates column by writing it -1.
Oh, okay. So we are taking only 3, like invest, consumption, and
yes. So suppose if date was the 5th column, I would write DF -5.
Okay, right? Because it is in first column.
Yeah, date is the first column. That's why I dropped it. So you have to drop it. Yeah. And then you need a date object. I need to order my data in some order of time.
Okay.
You see, now just compare this.
Order by date. Yeah.
Had DF?
The date is shown.
Had DF1. You see, now there is no date. Rather, date has gone to the index. There is no name for date, but dates do exist. They are there. Right?
So it is like a unique column which is being ordered.
Yeah, you can say, right.
Yeah.
Right. So this has converted into a matrix. So DF1 is a matrix. If I show you, this is an XTS object. Right? I did not talk about, see, it was a challenge for me to like strike a balance between R and econometrics. There is some preliminary information about R that I wanted to give. Like, how can we be more productive with R? There are 2 reasons. First of all, it is free. And second thing is that we can be more productive with R. Our analysis would be much faster. Time is very less. Else, I would discuss how can you just like prepare detailed reports in R. I'll show you some custom functions. Like initially we start working with R, then we start writing our own functions. The beauty is that all these longer functions can be like collapsed to very shorter versions. I'll share tomorrow.
Okay.
So let's get back to it. Same process, VAR modeling equivalent to AR modeling. That means identify, estimate, diagnostics. So let's identify the model. Again, that means we can make use of ACF, PACF plot, but in the case of VAR, they are like not possible. So what we do, we make use of information criteria. Okay. That means we run several models and we choose the model which has lowest value for these information criteria. So let's go to this package. Library wars that we have already run. Yeah, one thing is there. If I show you, look at this DF1. Not this, sorry. DF2. One second. One second. Yes, look at this. Not visible. You see, look at the first row.
First difference.
It's NA. The three values are lost cause of the first difference. If you plug in the same data, R will throw an error that missing values are not allowed. So what you're going to do, simply remove all the rows that have missing values. And the command is na.omit. So df2 is equals to na.omit df2. So in case you want to retain both the data frames, you can create a new object df3. df2, all the data points, including the first row that has NAs. But anyhow, how that row is important, I don't know. So there is no need for that. That's why I have written this df2. So df2 is the old df2 after removing missing values, na.omit. Now look at this function. IC equals to var select. So let's run this command. It has created an object called IC. Okay. And if I just like go to console and type summary, not this one. You see, R has printed a lot of output and it has given me the information criteria for like several methods, using several methods. So dollar criteria. So AIC is there, then HQ is there, hand and queen. This is the Schwartz information criteria. Then it is a FPE, finite precision error, I think. Okay. And what is the lowest value for each model? It is displayed on top. Look, for AIC, model 2 is best, and according to SC, model 2 is best. Mostly what happens whenever you do this test, then AIC tends to choose longer lags and SC tends to choose lower number of lags. And there is like no consensus among econometricians so far which method is better. So it's a matter of art, a matter of choice. So you may choose like lags even given by AIC or given by SC. These are more popular. But in the present case, both of them are same, fortunately. But mostly they are not. AIC gives much larger lags. Okay. So means how many lags are important? We are going to fit a trivariate var with 2 lags. Trivariate var. Why trivariate? We have 3 variables: income, investment, and consumption. Okay. So you can just print this information, IC dollar selection. Now look at the model. Model gets, again, instead of less dash, I can use equals to sign. Var is the function that will estimate the model data. Then P equals to means how many lags are we going to use? Then what do you want? Do you want intercept, trend, etc., etc.? So our model has been estimated. Okay. So now any idea like how many coefficients will be there in this VAR? We have estimated a trivariate VAR 2. Means for
Four.
we have
Two beta.
one equation for each variable. Sorry, total coefficients?
4, sir, including
Four,
constant.
Not
including
four.
constant.
Yeah.
No, no.
They won't be 4.
three,
2
three,
lakhs for
three
each
into-
variable. No, 2 for
Two.
each. For
Ah.
example, look at the equation for investment. It will contain 2 lakhs of investment, 2 lakhs of income, and 2 lakhs of consumption. And then
6,
one intercept, 7.
7.
7 in each equation. Then 7 in the equation for income. Then 7 in the equation of consumption. Right? And see, this is a that means very small. That means a small VAR. When you're working with like data which is daily in nature, lags maybe 5 or 6. So let's say there are 5 variables with 6 lags. So there are like 31 coefficients, right? But the good thing is that you should not think about analyzing the individual VAR coefficients. Let me just show you what the values are, but please do not ever interpret those values. Summary model, let's run this command, means we are printing out the model estimates for each equation. VAR estimation results. All the variables are endogenous. You see, all the roots are less than unity. So the way R calculates roots, they have to be less than 1. Right? Other software, they do it the other way. But I think most of the software, they present the information in such a way that if these roots are less than 1, then fine, else there is a problem. Okay, now look at this line, estimation result for invest.
Sir, could you please scroll up the screens?
Yes. Invest.L1, income.L1, cons.L1. L1 means lag 1. Invest.L2. Income. If you say I can enlarge this entire output, 1 second.
No, it's okay, sir. It's okay.
Yeah. There is a shortcut for it, Control-Shift-2, in case you want. Otherwise, see, but these coefficients are not at all important. I have seen many papers, like people try to interpret these coefficients, that 2 of them are positive significant, 2 are negative significant. So this has a positive impact, negative impact. So there is like no point of analyzing these coefficients. This is not multiple regression. In multiple regression, we need to talk about every coefficient. But when it comes to VAR, these coefficients are not at all important. They are important, but it is difficult to analyze them. There is a different way. We analyze them differently using impulse response function and forecast error variance decomposition. Those are the right approaches. So I'm just cleaning the console. I was just showing you that this system is quite large, right? So you need not even report it in your paper. In case you want, you can show these estimates. In your thesis, you can show these estimates, but again, do not interpret them. So let's go to, if you run this command, it will show you a plot. We have already seen it. Yeah, this one is important. So look what impulse response does. Impulse response means if there is a shock to any of the equation. Recall we have 3 equations, one for investment, then for income, then for consumption. Now there can be a shock in either of the equation. For example, suddenly government announces that everybody will be getting 5,000 rupees in their bank account. Means income of every person goes up. Right? This is a shock. Or let's say somehow there is recession and consumption goes down and income goes down. So these are like shocks, which are like which are some kind of surprises, right? So suddenly something jumps or something crashes, then these are the shocks. So when there is a shock in investment, how this shock influence investment, then how this shock influence income and consumption. This is the subject matter of impulse response function. So what is the mathematical trick? It's quite involved. Think it this way. Recall I told you that an AR model can be converted into a moving average model. Similarly, a vector autoregression model can be converted into a vector moving average model. Means in terms of its error terms. Now we can analyze the impact of a unit shock of an error on the system. Unit shock. But there is a problem with the unit shock. Imagine you are dealing with returns data. In returns data, a unit shock means a jump of 100%, which is implausible, does not make sense. Then what to do? A better way is that instead of analyzing unit shocks, we should analyze a one standard deviation shock. One standard deviation shock means if any of the endogenous variable, it has a shock of one standard deviation, how this shock transmits to the other variables in the system. So let's analyze them one by one. We can show this entire information in just one graph, but that would be quite clumsy, and I think there will be so many plots. So what we do, we just analyze them one by one. So we are creating an object called IRF model. We're taking our model, and our model name was model. And impulse equals to, that means we're trying to find out the impact of income. Okay, on what? Consumption. See, if you do not specify impulse and response, what R will do? It will show the graphs for all the variables, means that would be there would be 9 graphs. Impact of investment on investment, investment on income, investment on consumption, then impact of income on investment, income on income, then income on consumption, and lastly consumption, impact of consumption on investment, impact of consumption on income, and consumption on consumption. There will be 9 graphs. We are not interested in them. Maybe we are just interested in how does income influence consumption. Okay, so let's run this command and see what happens. Okay, yes, I think this graph is visible. See any graph? No. 1 second. Yeah, because I did not plot it. 1 second. 1 second. Okay, plot IRF. What about now? Is it visible? Yeah. Look at this graph. In this graph, you see there are 3 lines. I think one solid line, and then like some dotted lines or dashed lines are around it. So the black line is the main response of the variable to the shock. In the present case, our impulse is income and response is shock. Means if income changes by 1 standard deviation, how consumption behaves. Okay, so look at this. If you see it, initially there is a like positive response of consumption to a shock in income. Okay, and then suddenly it reaches to 0. You see, that means it reaches to 0. And you see the confidence interval. These 2 lines around the solid line, these are the confidence bands. These bands should both be in just one direction. Either they should be in the positive side or both of them should be in the negative side if the impact has to be significant. Look at lag 3. You see at lag 3, the one confidence band is negative, the other one is positive. When confidence is in both the region, that value is deemed to be 0. So I think it seems that there is the impact of shock on income on consumption is positive initially, but it dies out in the immediate next period. So it does not take much time that the response of consumption to income is, that means, absorbed in just 2 time periods. If you just look at the graph more closely, right? So similarly, we can make other plots. This is how we should interpret this variance impulse responses. Sometimes these graphs are like very difficult to interpret, but yes, you can take some hints from theory. And what we should do rather, we should worry about, you see that at lag 0, it is 0. The reason is that there is no way to find out the contemporaneous impact. That means if income changes, then how change in income immediately influence consumption? This can't be known. Why? Recall the equation of VAR. There was no contemporaneous term on the right hand side. We had only t minus 1, t minus 2, right? So this is why the shock can be felt in the next time period. Then there are orthogonal impulse responses to deal with this problem. But there is a challenge. The challenge is that the impulse response is sensitive to the ordering. Like, recall how the data was organized in our case. It was investment, then income, then consumption. Okay, so this ordering will become important. Means if you change the order, the shape of impulse response will change. So this creates a big problem for people. That means how do we analyze and how do we know like which model is correct? Then the answer lies in theory. That means theory should tell you that what could be the proper order. For example, I was working on a paper and wanted to find out relationship between like crude oil price, exchange rate, and stock market. Right. So during COVID, it was quite sensible. There was a shock in the crude oil. It even became negative in the futures market. So the price on crude oil, it was like transmitted on the stock market through exchange rate, because exchange rate were also very volatile during those days, right? So how does the stock market respond? How did the stock market respond? So in this case, the natural ordering was, logical ordering was first crude oil, then your exchange rate, and then your stock market. If you can give a reason some other way out, that if a stock market changes, then like foreign investment starts coming in, and then it can impact other stuff. So that means your theory should tell you what should be the ordering of the factors in your VAR system, right? So this is how we can just analyze VAR. Then very similar to VAR, we obtain information about what we say the forecast error variance. Like what we can do using these models, we can make forecast. Like what is the forecast for consumption in the next time period, after 2 time periods, after 3 time periods, after several time periods ahead, right? So those are the forecast, and we can compute the forecast error. We can compute forecast error, and we can determine the variance of that forecast error. Now, variance, the larger the variance of the forecast error, it means less reliable is the forecast, right? Now we can find out how much variance in the forecast error is caused by a particular factor. For example, let's say we're trying to forecast consumption. Okay, now consumption will have forecast error, and there is a variance associated with this forecast error. Now, what proportion of this variance is caused by income, what proportion is caused by investment, and what proportion is caused by consumption itself? So this information is helpful in determining like how much is the impact of a variable on other variable. So these are similar information, but yes, they are difficult to interpret. You can refer to your literature and then like take clues from there. How can you like interpret? How does the impulse response they become sensible? Sometime like some people have revised theories on the basis of impulse responses. Means theory was saying something else, but when it was analyzed in the system of VAR, the response was different than what theory was telling. Then people revise theories that okay, that means it's not the case that you must always be hell-bent on fitting with the theories. No, when something different than theory is happening, maybe the theory has changed, right? Because things are not static forever, they keep on changing, right? So we should not be just willing to replicate the results by others. We should not be saying okay, in theory there is always a negative sign. If you get a positive sign, try to weave a story around it. Why this positive sign? Can you just like justify it? Can you like bring support from some other discipline or maybe some new empirical evidence? Right, but it should not be implausible. If the result is like you are not able to explain and result is different, then it is incomplete story and nobody is interested in that. Your result is different and you have a good story to tell, then it becomes sensible. So we are able to cover just VAR. Okay, now accept any queries regarding VAR? I'm given further codes for like orthogonal impulse responses. Then let's move on to the next thing. Should we move on to co-integration?
Yes, sir.
Yes, sir. We will do it.
Okay. So recall what we did in VAR. We started with some variables like investment, income, consumption. Then we tested whether they are stationary or not. So VAR is basically based on stationary variables. But sometimes what happens, when we just take a system, then individual components are I1. For example, investment is, let's say, I1, consumption is I1, and your income is I1. They all are I1. But collectively, when we make a linear combination of them, that means investment plus income plus consumption, of course, in some specific scheme, let's say 2 times income plus 1.5 time investment minus 0.8 time consumption, kind of, for an example, if we make a linear combination, then it is possible that linear combination is stationary. First of all, what happens most of the time when you are combining I1 variables, I1 means non-stationary. When you are combining I1 variables, the result will be I1. Means combination of non-stationary variables is non-stationary as well. But there is a specific case. Sometimes what can happen that when you are combining the non-stationary variables, then there are some unique combinations which make the combination stationary. This is the idea behind co-integration. And why does this happen? This may happen like when two variables, they move simultaneously. There is co-movement between them. In short run, there are deviation, but in long run, like they cannot wander apart. Like think about the, let's say, real interest rate. People can say that interest rate and nominal interest rate and inflation, they are tied together. Similarly, think about this futures market and spot market. So you can buy the share of a company in spot market, or you can buy the same share, same stock in futures market. The company is same. The only difference of time. You can buy something today, you can agree to buy something 2 months later, right? So they should be related. That means their price cannot be different arbitrarily. There must be some force which is binding these prices not to wander apart wildly. That force is some economic theory. In the case of future and stock market, it is the cost of carry relationship. Similarly, in other cases, like there are theories in place, like this Fisher effect. In the case of this nominal interest rate and inflation, right? The theory given by Fisher is that the real interest rate is constant. Okay, you may test this hypothesis using data. So now, I'm taking this another data set. Should I quickly discuss about the theoretical framework of co-integration?
Yes, sir.
Yes, sir. Sir, one small doubt, like when
Yes, please.
it comes to co-integration, we
Hmm?
have one more, which is where vector error correction model. So
Yes.
is it that we may have to look that also in
Yes,
take that also in
when
consideration?
variables are co-integrated,
Yeah.
then the relationship we should model, it is in the form of vector error correction model.
Okay, only when they are
Yes,
co-integrated.
I'm just
But
showing you
R
basically.
has, okay,
Yeah, please
sir.
tell me, please.
R has that facility also, or?
Yes, it has.
Okay.
So let's talk about what co-integration is. I briefly told that two variables which are I1, two or more than two, but their linear combination is stationary. What a beautiful result. Otherwise, when you combine two non-stationary variables, the new variable will be non-stationary as well. But if they are co-integrated, then though they are I1, but their combination is I0. So look at this model. This is a simple var. I think you all are able to recognize this is just var, right? So the thing is that this y is a vector. Is m by 1 vector, means there are m variables. If m is equal to 3, means there are 3 variables, y1, y2, y3. If m is equal to 6, there are 6 variables, y1, y2, y3, y4, y5, y6. Okay. So now this is a var. But the problem is that this var is meaningful only when the individual components of y vector are stationary. Like this y can be vector that has, let's say, your consumption, investment, and income, right? So all these 3 variables, consumption, income, investment, they must be stationary. So they are called the component of a vector. So they can be the interest rates, they can be just the prices, it can be anything. Okay, this var is meaningless. Now, when things are like non-stationary, the usual practice is that we have to difference the data, difference it, convert it to first difference, return series, and then model it. But there is a better way. What we can do, we can transform this model, like by subtracting and adding and subtracting some of the terms. What we can do, we can transform this model, and this model will become like this. So Engel and Granger, they suggested a transformation. Both of them were Nobel laureate. Look at this. The earlier var is converted into this equation. We call it the transformation. So now see, earlier, we have used different symbols. The first symbol on the right hand side is pi, capital pi, and then we have like gamma 1, gamma 2. This is a Greek letter, capital gamma, right? And the way we have applied the mathematical trick is that where so pi is governed by this relationship and gamma by that relationship. So pi and gamma are governed by this relationship, and this IM is an identity matrix, right? Now look at this system. Look at the system. You see, earlier we had variable y, and y was non-stationary. But now look at this equation, we do not have y. Mostly we have delta y. Delta y is, of course, stationary. But there is just one variable. Look at the first part. There is pi, capital pi, yt minus 1. Equals cap pi, yt minus 1. This is the main trick in co-integration. Means all the variables are stationary except this. Now, this pi yt minus 1 can be thought of as a linear combination of variables in y. Now, if this particular becomes stationary, if this becomes stationary, then it means that variables are co-integrated. And if does not become stationary, it means they are not co-integrated. So Soren Johansson and Katrina Juselius, they devised this idea that we can test whether there is co-integration by looking at the rank of this matrix. Now, what is the rank of a matrix? Rank of a matrix is the number of independent rows or the number of independent columns. Means number of columns which are not linearly dependent on one another, right? So we will investigate the rank of this matrix. Suppose the rank of this matrix is 0. If rank of this matrix is 0, the conclusion would be there is no co-integration. If the rank of the matrix is 1, it means there is like one combination that is stationary, one way of achieving co-integration. If the rank is 2, it means there are 2 ways of achieving co-integration. If rank is 3, there are 3 ways of achieving co-integration. But of course, the rank of this matrix cannot be larger than the number of the variables, right? If there are 6 variables, we can have at most 5 relationships, 5 co-integrating relationships. We cannot have 6. If we have 2 variables, only 1 co-integration is possible. If we have 3 variables, maximum 2 are possible. If we have 4 variables, then maximum 3 are possible. Less than 1 co-integration is possible. So idea is quite simple. We just need to identify the rank of this pi matrix. Mathematically, it's quite tough, but software will do it. We just need to look at the significance. Okay. So we need to examine this pi matrix, and we have 2 test statistics. One is called the trace test. The other one is called the eigenvalue test, maximum eigenvalue test. So let us go to our data.
Sir, may I interrupt you for
Please.
just 1 minute? Thank you, sir.
We'll start tomorrow. Thank you.